Hello everyone. Have you ever wondered there are so many elements in our periodic table, but still they show different kinds of behaviors? Do you want to know the reason? Yes, sir. Yes, sir. We want to know the answer. Where is the answer, sir? Great. Sounds interesting. You are a curious student. The answer is inside the atom. What, sir? Inside the atom? In last chapter, you said that matter has smallest unit which is called atom. It came from Greek word atomia, which means that it is non-divisible. And now you are saying that the answer is inside the atom. Sir, you are only increasing our syllabus, sir. Yes, yes, you said the correct definition of atom. The atomic theory of matter was first proposed on a firm scientific basis by John Dalton, a British school teacher in 1808. His theory called Dalton's atomic theory. You know the theory? Yes, sir, yes, sir. I remember that. And due to the theory of law of conservation of mass, I knew why it is necessary to balance a chemical equation. And I also learnt more theories like law of constant proportion, law of multiple proportion. Yes, sir, now I remember the theory. Yes, the theory was very important for chemistry. However, it failed to explain the results of many experiments. Do you want to see the experiment? Okay, now we will take a look of that experiment. Okay, now I know. But when scientists knew that there is something inside the atom, this is the thing we are going to study in this unit. We are going to start with the experimental observations made by scientists towards the end of 19th and beginning of 20th century. This established that atoms are made of subatomic particles, that is electrons, protons and neutrons, a concept which is very different from that of Dalton. Discovery of electrons and Thomson's atomic model. Many scientists contributed in revealing the presence of charged particles in an atom. Now let's learn discovery of subatomic particles. It was known by 1900 that the atom was not simple indivisible particles but contained at least one subatomic particles. It was known by 1900, remember. Who is he? It's Sir J. J. Thomson. A British physicist was born in Cheetham Hill, a suburb of Manchester, on October 18, 1856. He was awarded the Nobel Prize in Physics for his work on the discovery of electrons. He directed the Cavendish Laboratory at Cambridge for 35 years, and seven of his research assistants subsequently won Nobel Prizes. So now we are going to learn Thomson's atomic model. So now we are looking this figure. Thomson passed electricity at high voltage through a gas at very low pressure taken in this discharge tube. Streams of minute particles were given out by cathode. Now look carefully in this figure. Cathode is negative and anode is positive. So cathode is a negative electrode. These streams of particles are called cathode rays because they come out of cathode. Cathode rays consist of small negatively charged particles called electrons. Since all the gases form cathode rays, it was concluded that all the atoms contain negatively charged particles called electrons. Canal rays, protons, and characteristics. Okay, what is this? Seems like a pudding. Yes, Thomson proposed the model of an atom to be similar to that of a Christmas pudding. The electrons in a sphere of positive charge were like a currants, that is dry fruits, in a spherical Christmas pudding. Just like this. These are the electrons, negatively charged electrons, and positively charged matter. While the electrons are studied in the positively charged sphere, like the seeds in the watermelon, negatively charged seeds and positively charged matter, just like this. Thomson proposed that an atom consists of a positively charged sphere and the electrons are embedded in it, just like this watermelon. Here is positive, red color shows positive charge and the seed shows negative charge. Electron. The negative and positive charges are equal in magnitude, so the atom as a whole is electrically, yes, if negative and positive charges are equal, it will be electrically neutral. Neutral means having no charge. Now we are going to learn characteristics of electron. Now we are going to learn characteristics of electron. First of all, we are going to learn mass of an electron. The mass of an electron is about 1 upon 1840 of the mass of hydrogen atom. Means it is so small that it is considered to be negligible. Now charge of an electron. The absolute charge of an electron is 1.6 into 10 raised to minus 19 coulomb of negative charge. The relative charge of an electron is minus 1. E. Goldstein discovered the presence of new radiations in gas discharge and called them canal rays. He is E. Goldstein. These rays were positively charged radiations. This subatomic particle had a charge equal in magnitude but opposite in sign to that of electron. Its mass was approximately 2000 times as that of electron. It was given the name as proton. Now slowly we are knowing each and every subatomic particle. So proton will be represented as P. Now we are going to learn characteristics of proton. The two important characteristics of a proton are its mass and its charge. Here is the diagram in which proton and electron are shown. Mass of a proton. The proton is actually a hydrogen atom which lost its electron. What is proton? It is a hydrogen atom which has lost its electron. Means if anything loses negative, it will attain positive. The relative mass of a proton is 1 U, that is 1 unit. Charge of a proton. The charge of a proton is equal and opposite to the charge of an electron. That's why we are going to learn that atom will be electrical neutral. So the absolute charge of a proton is 1.6 into 10 raised to minus 19 coulomb of positive charge. In other words, the relative charge of proton is plus 1. Now next point is Rutherford's gold foil experiment and its drawback. He is Ernest Rutherford. He was born at Spring Grove on 30th August 1871. He was known as the father of nuclear physics. Remember my friend, who is known as father of nuclear physics? The answer is Ernest Rutherford. He is famous for his work on radioactivity and the discovery of the nucleus of an atom with the gold foil experiment. He got the Nobel Prize in Chemistry in 1908. Now we are going to discuss Rutherford's model of an atom. Ernest Rutherford was interested in knowing how the electrons are arranged within an atom. Rutherford designed an experiment for this. In this experiment, fast moving alpha particles were made to fall on a thin gold foil. Alpha particles in a positively charged particle having 2 units of positive charge and 4 units of mass. Now we are going to discuss about gold foil experiment. Take a source of alpha rays. They are beam of positively charged particles. What is this? It is a gold slit. In front of the source, we have to keep the thin gold foil. Gold foil means thin sheet made up of gold. Now keep screens to detect the alpha rays. These are the two slits. Now the positive rays are being passed. The first ray passes through the gold sheet. Let's see the reason behind this by performing a simple experiment. Stand near a fence and throw a stone towards the fence. The first the first ray passes through the gold sheet, just like this stone is passing through this fence. The stone passes through the fence to the other side. Why does this happen? Because there is a lot of empty space between the two planks of the fence, hence the stone passes through the fence. Similarly, in gold atom, there is a lot of empty space from where the alpha rays passes. Now again, what happened? The second ray hits the gold foil and turns back. Let's see the reason behind this. Now again, the same experiment. The boy is throwing stone onto the fence. This and the second stone hits the fence and turns back. Why does this happen? This happens because the stone hits the plank and doesn't allow the stone to pass through. Similarly, in gold atom, there is a positively charged part which turns the positively charged alpha rays. Positive will repel positive. So finally, what will happen here? These are the rays. Majority of rays passes through the gold sheet. This shows that the part from which the positively charged alpha rays turns back is very small in size compared to the empty space. So what is the conclusion of Rutherford's alpha particle scattering experiment? It shows the presence of nucleus in the atom. Yes, there is a nucleus in this atom. It also given the following important information about the nucleus of an atom. Nucleus of an atom is positively charged. Nucleus of an atom is very dense and hard. But the nucleus of an atom is very small as compared to the size of the atom as a whole. The radius of nucleus has been found to be 10 raised to 5 times smaller than the radius of an atom. Just like in this cricket stadium, the relative size of the nucleus in an atom is roughly as same as that of a pea in the middle of this large stadium. Now, what are the drawbacks of Rutherford's model of an atom? A major drawback or defect of Rutherford model of an atom, it does not explain the stability of an atom. Any particle in circular orbit would undergo acceleration. During acceleration, charged particles would radiate energy. Thus, the revolving electron would lose energy and finally fall into the nucleus. If this were so, the atom would be highly unstable and hence matter would not exist in the form that we know. But we know that atoms are quite stable. So that's why here comes the next theory, Niels Bohr atomic model and electronic configuration. In order to explain the stability of an atom and overcome the objection against Rutherford's model of atom, Niels Bohr gave a new arrangement of electrons in the atom in 1913. Niels Bohr explained the stability of atom. Niels Bohr was born in Copenhagen on 7th October 1885. He was appointed professor of physics at Copenhagen University in 1916. He got the Nobel Prize for his work on the structure of atom in 1922. Among the Professor Bohr's numerous writings, three appearing as books are The Theory of Spectra and Atomic Constitution, Atomic Theory, and a Description of Nature. Now let's see the Bohr's model of an atom. In order to overcome the objection raised against Rutherford's model of the atom, Niels Bohr put forward the following postulates about the model of an atom. The first postulate was only certain special orbits known as discrete orbits of electrons, are allowed inside the atom. While revolving in discrete orbits, the electrons do not radiate energy. These orbits or shell are called energy levels. These orbits or shell are represented by the letters K, L, M, N, or the numbers n is equal to 1, 2, 3, 4. Now there is a simple formula. There is a limit to the number of electrons which is energy level or shell can hold. The maximum number of electrons which can be accommodated in the energy level of the atom is given by 2n square, where n is the number of that energy level. For example, k shell 2n square, in that k shell it is the first energy level. So 2 into 1 square, that is 2. So in k shell 2 electrons. L shell 2 into 2 square, 8. Then M shell 2 into 3 square, that is 18. And N shell 2 into 4 square, that is 32. So this is the simple rule which is given by Niels Bohr. Now module 6, electronic configuration of first 18 elements. Comparison of atoms of the first 18 elements with electron distribution in various shells. The first is hydrogen, as we know the symbol is H, atomic number is 1, distribution of electrons 1, so it will be in the first shell, H like this 1. Second helium, He2, these two electrons will also be in the second shell, first shell, He. Now here comes lithium. Lithium has 3 electrons, so in the first shell there will be 2 electrons and in the second shell there will be 1 electron. Similarly for beryllium, atomic number 4, so first shell 2, second shell 2, it will be like this. For boron 5, so it will be 2, 3, in the first shell 2, second shell 3. Carbon C, atomic number 6, it will be first shell 2, second shell 4. Nitrogen, first shell 2, second shell 5. Oxygen 8, first shell 2 and second shell 6 electrons. Now the next element is, yes, that is fluorine. It has atomic number 9. So first shell 2 electrons and second shell 7 electrons. Neon 10. In the first shell it is completely filled, that is 2 electrons, and second shell also completely filled in neon, which contains 8 electrons. Now here comes the third shell if we are going to study the next elements. Sodium Na 11, in the first shell 2 electrons, second shell has limit of 8 electrons, so 8 electrons, and in the third shell 1 electron. So it will become like this, Na. Magnesium Mg12, so 282, it will be like this. Similarly, aluminium 13, 283, like this. Silicon Si14, 284, just like this. Phosphorus P15, 285, it will be like this. And sulfur S16, 286, it will be like this. Chlorine 17, 287, so in the first shell 2, second shell 8 and third shell 7. And argon Ar 18, so in the first shell 2, second shell 8 and third shell also 8. Discovery of electrons and its characteristics. He is James Chadwick. James Chadwick was born in Bollington, Cheshire on 20th October 1891. In 1932, James Chadwick discovered another subatomic particle which had no charge and a mass nearly equal to that of a proton. It was eventually named as neutron. Neutrons are present in the nucleus of all atoms except hydrogen. In general, a neutron is present as n in the mass of an atom, is therefore given by the sum of the masses of protons and neutrons present in the nucleus. Characteristics of neutron, mass of neutrons. In this figure, here these are electrons, yellow are electrons, green are protons and red are neutrons. The mass of neutrons is equal to the mass of proton. The relative mass of neutrons is 1 unit. Charge on neutrons. Neutron has no charge. It is electrically neutral. The next concept is atomic number and mass number. Atomic number. It is the number of protons of an atom. which determines its atomic number. It is denoted by Z, all atoms. All the atoms of the same element have the same number of protons in their nuclei, and hence they have the same atomic number. No two elements can have same atomic number. Atomic number can be used to identify an element. The atomic number of carbon is 6. So for carbon, Z is equal to 6. Atomic number tell us that it is carbon element. No other element can have atomic number 6. In a normal atom or neutral atom, the number of protons is equal to the number of electrons in it. So we can say that the atomic number of an element is equal to the number of electrons in a neutral atom. Now what is mass number? Mass of an atom is practically due to protons and neutrons alone. Mass of an atom is practically due to protons and neutrons alone. These are present in the nucleus of an atom. Hence protons and neutrons are also called nucleons. For example, mass of carbons is 12 units because it has 6 protons and 6 neutrons. So 6 plus 6 unit, it gives 12 units. Here it is. Red are the protons, black are the neutrons, and electrons are revolving like this. So it is representing carbon. So 2 electrons revolving in the first orbit and 4 electrons are revolving in the second orbit. And how many protons and how many neutrons are there? Yes, 1, 2, 3, 4, 5, 6. 6 protons and 6 neutrons. Similar, the mass of aluminum is 27 units because 13 protons and 14 neutrons. Just like this. In aluminum atom, there are 13 protons and 14 neutrons. The mass number is defined as the sum of the total number of protons and neutrons present in the nucleus of the atom. The mass number of an element is denoted by the letter capital A. In the notation for an atom, the atomic number, mass number and the symbol of the element are to be written as like this. Mass number, symbol of the element and atomic number. A, Z, X, where A is the mass number, X is the symbol of element and Z is the atomic number. For example, nitrogen will be written as 14N7. It means that 14, its atomic mass, N means nitrogen, symbol of nitrogen, and 7 its atomic number of nitrogen. Relationship between mass number and atomic number. Mass number is equal to number of protons plus number of neutrons. Since the number of protons in an atom is equal to atomic number of that element, we can rewrite the above relation by putting atomic number in place of number of protons. So mass number is equal to atomic number plus number of neutrons. Now let's solve few numericals based on atomic number and mass number. Sample problem 1. Calculate the atomic number of an element whose atomic nucleus has mass number 23 and neutron number 12. What is the symbol of the element? Now look carefully. Whose atomic nucleus has mass number 23 means that element's mass is 23 and neutrons are 12. So how many protons will be there? Total mass is given. Protons, as we all know, protons plus neutrons is equal to mass number, or atomic number plus neutron is equal to mass number. So X, let's suppose, let's solve this problem. We know that mass number is equal to atomic number plus number of neutrons. So 23 is equal to atomic number plus 12. So atomic number is equal to 11. So 11 is atomic number of sodium. The element having atomic number 11 is sodium and its symbol is Na. If however we indicate the atomic number and mass number also, then the symbol become 23 Na11, where 11 is the atomic number and 23 is the mass number. Next problem. Helium atom has an atomic mass of 4 units and 2 protons in its nucleus. How many neutrons does it have? It is very simple. We know that atomic mass is numerically equal to the mass number of an atom. Since helium atom has atomic mass 4 units, therefore the mass number of helium will be 4. The number of protons in the helium nucleus has given to be 2. Now, mass number is equal to number of protons plus number of neutrons. So 4 is equal to 2 plus number of neutrons. Number of neutrons is equal to 4 minus 2, that is 2. The helium atom has 2 neutrons. Our next concept is isotopes and different examples for hydrogens. What is meant by isotopes? Let's see first for hydrogen. Hydrogen has 3 isotopes: protium, deuterium and tritium. Now look, if you look carefully, all the 3 isotopes have Z is equal to 1, but it has different A. So we can say that isotopes means the elements which have same atomic number. Again I am saying same atomic number but different mass number. Isotopes are the atoms of the same element having same atomic number but different atomic mass number. So the example is, another example is of carbon C12H6, 12C6. So atomic mass number is 12, atomic number is 6. So number of neutron will be 6. Now 14C6, mass number is 14, atomic number is 6. So the number of neutrons is 8. Next, what will be the element then? Cl, 35Cl17. So mass number is 35, atomic number is 17. So number of neutrons 35 minus 17 will be 18. 37Cl 17, again 37, 17, 37 minus 17 it will be 20. Okay. So number of neutrons in the isotopes is different because its atomic number will be same. As we all know, atomic number for each individual element is same. Okay. So what are the so chemical properties of isotopes will be same. Now the diagrams of 2 isotopes of chlorine are given below. Now here nucleus contains 17 protons and 18 neutrons. This is Cl35 isotope, mass number or atomic mass is 35. And here nucleus contains 70 protons and 20 neutrons. So P and N are shown here. So Cl37 isotope, mass number or atomic mass is 37. Mass number of an atom is equal to its atomic mass. Again I am saying mass number of an atom, it's equal to its atomic mass. Isotopes of hydrogen. The hydrogen element has 3 isotopes having the same atomic number 1 but different mass numbers 1, 2 and 3 respectively. So it will be 1H1, 2H1 and 3H1. So they are like protium 1H1, 1 proton, 1 proton, 0 neutron and 1 electron. Deuterium 2H1, 1 proton, 1 neutron and 1 electron. Tritium 3H1, 1 proton, 2 neutrons and 1 electron. It is clear from the above table that all the isotopes of hydrogen contain 1 proton and 1 electron each, but they contain 0, 1 and 2 neutrons respectively. So isotopes exist due to different number of neutrons. Again we are revising the same concept again and again with the different examples. The diagrams of 3 isotopes of hydrogens are given below. This is for ordinary hydrogen or protium, atomic mass 1 unit. This is for heavy hydrogen, deuterium, atomic mass 2 units. This is for very heavy hydrogen, tritium, atomic mass 3 units. So first one contain 1 proton only, second one contain 1 proton, 1 neutron, and third one will contain 1 proton, 2 neutrons. Now isotopes of carbon, oxygen and neon. The carbon element has 3 isotopes having the same atomic number 6 but different mass numbers like 12, 13 and 14. The 3 isotopes of carbon can be written as like this. First carbon 6 protons, 6 neutrons, next carbon 13, 6 protons and 7 neutrons, and carbon 14, 6 protons and 8 neutrons. So first one will be written like this, 12C6, next one 13C6 and next one 14C6. So 6 is atomic number, that is number of protons. All the isotopes of oxygen have the same atomic number 8, but they have different mass numbers or atomic masses 16, 17 and 18 respectively. It will be written like this. O16 isotope, O17 isotope, and O18 isotope. First on in all the isotopes, number of protons are 8, but number of neutrons are increasing, like 8, 9, and 10 respectively. So it will be 16O8, 17O8, and 18O8. So 8 is same. It will be number of protons or atomic number. Since the masses of the isotopes of an element are slightly different, therefore the physical properties of the isotopes of an element are slightly different. The various isotopes of an element can have slightly different physical properties such as densities, melting points, and boiling points. It is obvious from the above symbols that all the isotopes of neon have, now look carefully for the symbols. It is obvious from above symbol that all the isotopes of neon have the same atomic number 10, but they have different mass numbers or atomic mass 20, 21, and 22 respectively. The chemical properties of an atom of the element depend upon the number of protons and electrons, not on the number of neutrons. Again, I am saying physical properties can slightly change, but chemical properties of an atom will depend upon protons, number of protons, and number of electrons, and not on the number of neutrons. Okay, because neutrons do not carry any charge. Since all the isotopes of an element contain same number of protons and electrons, the chemical properties of all the isotopes of an element are identical or same. Next, isotopes and their application. The chlorine isotope 35Cl17 has a mass of 35 units and its abundance or proportion in nature is 75%. The chlorine isotope 17Cl17 is in proportion in 25% in the nature. The average atomic mass of chlorine atom on the basis of above data. Again, I am saying in nature there are the chlorine 35 isotope has 75%. So we have taken 75 here, 75 upon 100, 35 into 75 upon 100 plus 35, and the chlorine 37 isotope has 25% abundance. So 37 into 25 will be taken. So 37 into 25 upon 100. So how we will solve this? It will be the average atomic mass. So the total average atomic mass of chlorine atom will be 35.5 units. So remember my friends, in our periodic table the values of atomic masses are written in points due to it is calculated average atomic mass. Okay. This does not mean that any one atom of chlorine has fractional mass of 35.5 units. It means that if you take certain amount of chlorine, it will contain both isotopes of chlorine and the average atomic mass is 35.5 units. Bromine occurs in nature mainly in the form of two isotopes, 79Br35 and 81Br35. If the abundance of 79Br isotope is 49.7 and the 81Br35 is 50.3%, calculate the average atomic mass of bromine. So how we will calculate? We know that the upper digit in the symbol of an isotope represents its mass, which is the same as its mass number. Now, the mass of 79Br35 isotope is 79 units and its abundance is 49.7%. The mass of 81Br35 isotope is 81 units and its abundance is 50.3%. So 79 into 49.7 upon 100 plus 81 into 50.3 upon 100. So it will be 3926 upon 100 plus 4074.3 upon 100. Final calculation will be 3926.3 plus 40.743. So it will be 80.006. So approximately it will be 80 units. So it is 80 units is the average atomic mass of bromine. Now applications of radioactive isotopes. First is uranium. Uranium 235, that is 235U, is used for nuclear fission and production of energy in nuclear power plants. Isotopes of some elements are used in the medical treatment of deadly diseases like cancer. Now applications of radioactive isotopes. Iodine 131I is used in the treatment of goitre, a disease of thyroid gland. Next is radioactive isotopes are used in industry to detect the leakage in underground oil pipelines, gas pipelines and water pipe. Next is isobars. Let us consider two elements. Atoms of two different elements having different atomic number but same atomic mass number. For example, argon and calcium. Argon contains 18 protons and calcium contains 20 protons. Argon contains 22 neutrons and calcium contains 20 neutrons. So the mass number will be 40 and 40. Which two of the following atomic species are isotopes of each other and which two are isobars? So the question is 231Z90, 230Z91, 230Z88 and 230Z90. As we all know, the upper side is its mass, atomic mass, and lower side is its atomic number. So the two elements which have same atomic number but different atomic mass, so the first one and fourth one are the isotopes of each other, and the remaining are the isobars. So how we will solve? If the isotopes of an element have the same atomic number but different atomic mass numbers, the lower figure in the above given symbols indicate the atomic numbers. In this case, there are two atoms having the same atomic number 90. So there are two isotopes will be 231Z90 and 233Z90. Isobars have different atomic numbers but same mass numbers. The upper figures in the given symbols indicate the mass numbers. In this case, there are two mass numbers of 230. So the two isobars will be 230Z91 and 230Z88. Thank you. If you like the channel, kindly subscribe the channel. Thank you so much.